Well, I guess it is time. I hope people are staying warm. I will warmly welcome David for his talk.
Okay, thank you for the invitation. Glad to give a talk. So my talk is about tautological classes of definite four manifolds. So I'll get started. So first I have to tell you what tautological classes are, and then we'll look at them for definite four manifolds. So basically we're interested in families of manifolds. So basically what I have in mind is, well, I have a manifold X, and then I have a smooth family with fibers X over a base B. So my base and my fiber are going to be compact smooth manifolds, and my family is a smooth locally trivial fiber bundle with fibers X. And then, so of course the natural goal would be to classify smooth families over a given base with a given fiber, which is it's kind of analogous to classifying vector bundles over B, but of course it's generally it's harder than doing that. So of course it's, in general for most B's and most X's, it's kind of pretty hard to classify all the families, pretty much impossible. So what you can do is you can look at characteristic classes. So even for vector bundles, it's hard to classify them over a given space, but you can go a long way looking at the characteristic classes. So basically, well, not just for vector bundles, but for principal G bundles. So suppose I've got a topological group G that has a classifying space BG, and characteristic classes are basically cohomology classes of BG. So in particular, if I have a family with fibers X, you can think about that as just the associated fiber bundle of a diff bundle, of a principal diff bundle, where diff is the diffeomorphism group of X. And so you can look for characteristic classes, and those are just cohomology classes of B diff. And for simplicity, I'm gonna just consider rational coefficients, because already that's quite complicated. Yeah, so we are looking at cohomology classes of B diff. So all right, first place to start off would be if our fiber is a compact oriented surface. Well, I suppose you could start off with one-dimensional fibers, which would just be circle bundles, which is pretty straightforward. So move up to the next dimension is surfaces. And here we actually know a lot about B diff. So B diff is homotopy equivalent to the classifying space of the mapping class group, B gamma G. And it's rational homotopy equivalent to the moduli space MG of curves. Basically, you consider Teichmuller space, which is contractible, then the mapping class group acts on that, and it doesn't quite act freely, but it only has, the stabilizers are all finite. So basically, rationally, it's as good as a free action. And so the quotient, so rationally, the quotient is like the classifying space. So cohomology of B diff is the same as cohomology of the classifying space of the mapping class group. And that's also the same thing as cohomology of this moduli space of curves, MG. So this last object here, the cohomology of this moduli space has been, well, very intensively studied. A lot is known about it, but a lot is not known about it. And so people focus on a subring of this cohomology called the tautological ring. And when we look at tautological classes, it's going to sort of be a generalization of this tautological ring for surfaces. So this tautological ring is generated by these tautological classes, or Miller-Morita-Mumford classes. So I'll give you the general definition in the next slide. Basically, so what that gives you, the tautological ring is just the ring generated by these classes. So of course that gives you a map from the polynomial ring just in those variables, kappa 1, kappa 2, etc., into the cohomology of MG. And then the Madsen-Weiss theorem says that if you fix degree and G is large enough, then this map is an isomorphism. So in fixed degree and large enough genus, the characteristic classes are all tautological classes. Okay, so now I'll tell you what the tautological classes are in the general context. So we have once again a family E over base B with fibre X. And now I'm going to assume that it's fibre-wise oriented. Then, so the tautological classes or generalized Miller-Morita-Mumford classes are defined as follows. So take a characteristic class for the special orthogonal group, and then you apply that characteristic class to the vertical tangent bundle. Okay, so the vertical tangent bundle is just the tangent bundle of the fibers. Apply this characteristic class, integrate it over the fibers, and you'll get a cohomology class in the base. And so you can do this for any family, and the classes that you get are characteristic classes, which mean that they are pullbacks under the classifying map of corresponding classes in BDiff. Okay, so basically every characteristic class for SON is going to give me a cohomology class in BDiff, and those are the tautological classes. So then you can define the tautological ring as just the subring of the cohomology of BDiff, which is generated by those classes, and we call that the tautological ring of X. So when we look at tautological classes, there's kind of there's a very big difference between what happens if the fibers are even dimensional or the fibers are odd dimensional, because you know, all the cohomology of BSO is concentrated in even degrees. So these C's are always even. And so if X is even dimensional, when you integrate, you get something even dimensional. And hence they all commute. But if X is odd dimensional, then the tautological classes are all going to be odd dimensional. And so you know, whether X has even or odd dimension is going to make a big difference. We're going to be interested in the even dimensional case. So our tautological classes are all commuting. And so there's this theorem of Galatius and Randall-Williams, which is this sort of big generalization of the Madsen-Weiss theorem. So for all even dimensions bigger than or equal to 6, of course, that excludes 4. So basically the theorem says something like up to some stabilization, which is like connected sums of products of spheres, the characteristic classes are tautological. So this is sort of a motivation for studying the tautological ring, because in some sense it's like it's sort of the most stable part of this cohomology. Okay, so then what is known about tautological rings? Well, not a lot in dimensions bigger than 2. So for example, if you take a 2n sphere, then it's not too hard to figure out what happens. It's just sort of a simple exercise, and you can see that it's just a polynomial ring generated by kappa EP1 up to kappa EPN. If you take a product of n spheres where n is odd, then you get something, well, it's not known what it is, but if you take the reduced ring, so you mod out by the nilpotence, then you just get Q. And if we look at 4 manifolds, then not much is known. So I'll tell you now what is known about dimension 4. So first of all, note if we're in the 4-dimensional case, then the cohomology of BSO4 is just generated by P1 and E, and of course P2 is E squared. So tautological classes are just going to be linear combinations of these guys. So kappa P1 to the A, E to the B for integers A and B. Okay, so you can look at the 4 sphere, and again, that's just sort of a simple calculation. Basically, because the 4 sphere doesn't have much cohomology, there's not much that can happen, and you can just sort of figure it out. And it's just this polynomial ring. For K3, so there's this result of Jiran, Siracusa, Coopers, and Shishku. Basically, if you look at, so you look at the Herzebruck L polynomials, okay, and then you take the corresponding tautological classes where I is in this range 1 to 8. They showed that these classes are not 0. On the other hand, there is an argument which basically uses the sort of the family signature theorem, which tells you that these classes are nilpotent. So even though I can't tell you much about the tautological ring of K3, I can tell you that it has nilpotent elements in it. And so Randall-Williams investigated tautological ring for CP2 and S2 cross S2. He wasn't able to completely determine their structure. However, he did prove that, so the tautological ring of S2 cross S2, its Krull dimension is 3 or 4, but we don't know which. So that's kind of, it gives you an idea of sort of how much or how little we know about these tautological rings. Yeah, so what I'm going to do now is just kind of a warm up before getting to the main results. So I want to discuss sort of linear families of CP2. So what I mean by linear family is, suppose you've got a complex rank 3 vector bundle. Just for simplicity, I'm going to say its first Turing class is 0. Then you can take the sort of, and then you can take the projective bundle, which is a family of CP2s. So I'll call that a linear family of CP2s. So just as sort of a warm up, we're gonna look at the tautological classes for such a family. All right. So how do you compute the tautological classes? First, you want to work out the cohomology ring of E, and then you want to work out what P1 and E are for the vertical tangent bundle. So okay, this projective bundle has sort of a tautological line bundle over it, sort of O1, which is the hyperplane line bundle, and let X be the first Chern class of that line bundle. Then you have, well, X cubed. Basically, X satisfies an equation whose coefficients are the Chern classes of V. In fact, this is sort of the Grothendieck definition of the Chern classes. So basically, what you conclude is that the cohomology of such a family is going to be take the cohomology of the base. Well, sorry, take polynomials in X with coefficients in the cohomology of the base, and then divide out by this cubic equation. And the next thing we have to do is compute the Pontryagin class and the Euler class. So so you have the Euler sequence, which describes the vertical tangent bundle. So you have the trivial line bundle, and then you have V, which was our original vector bundle, tensor with O1 goes to T. So the Chern classes of T are just going to be the Chern classes of V tensor O1, and then you can use that to compute P1 and E, and you just get these simple formulas. So P1 is 3x squared plus 2b, and E is 3x squared take b. So the tautological class corresponding to P1 to the A, E to the B is just this Fibre integral of this class to the A times this class to the B. And then of course you could expand that out. That's just some big polynomial in X. And then it's easy to do the Fibre integrations because, so the Fibre integrals of 1 and X is 0, the Fibre integral of X squared is 1, and the Fibre integral of higher powers of X, basically what you do is you just keep using this cubic relation to get down to lower and lower powers of X, so you can compute all of these. And so, you know, it's quite a long computation, but you can do it in principle. And basically what you'll get is you'll get some polynomial in B and C. So recall, let me just remind you, B and C were basically, so B was minus the second Chern class and C was minus the third Chern class. So basically these tautological classes here are just polynomials in the Chern classes. And this phi, well, so here's some examples. So for P1 squared, it's 21b, P1 cubed, 117b squared, and so on. So you get some very strange looking formulas, but that's what it is. Now I don't know an explicit formula, but I know some recursive relations, which I've written down here. So basically, so yeah, you could compute any of these tautological classes by just using these recursive relations. All right, so that's the case of a linear CP² family, and now I'm going to talk about the main results.
David, I think you've got a question.
Yeah, may I ask you something? In the previous formula, if you have C, so if C happens to be 0, so can you have explicit formulas for
if C is 0? Probably yes. So I haven't sat down and I haven't done that, but if C is 0, then I mean this polynomial has to be sort of homogeneous if you give B and C the right degrees. So then it will just be some multiple of some power of B, and I think you probably could figure out what that coefficient is. I haven't sat down and done it, but probably yeah, you could.
And one more question. So did you look at particular base? Which would
so here at the moment it's B could be anything.
Okay.
So this is just, these formulas are kind of universal.
Okay, thank you.
Yep. Okay, so now I get to the new results. So basically we're going to consider a family of definite 4 manifolds. So basically that means, so the fibers are going to be compact, smooth, simply connected, positive definite 4 manifolds. So the definite meaning their intersection form on H2 is positive definite. And of course, by combining Donaldson and Friedman, we know that it's going to be homeomorphic to a connected sum of CP2s, where n is the second Betti number. And it's an open problem whether such a 4 manifold admits any other smooth structures. So for the purpose of this talk, you could assume X is just this connected sum of, oh, sorry, this n should be a 2. it could have some other smooth structure on it. And the result is going to be a kind of a diagonalisation theorem for the tautological classes. So the theorem is a bit complicated to state, but basically what it says is that the tautological classes of such a family behave as if it was a connected sum of linear CP2 families. So a linear CP2 family just means one associated to a principal PE3 bundle. So yeah, so let X be a definite 4 manifold. Consider a family of fibers X. Assume there's no monodromy. I mean, assume the monodromy acts trivially on H2. Then there exist classes B1 up to Bn and C1 up to Cn, such that the tautological classes of E look like a sum from 1 to n of phi. So this phi is the same phi we had in the linear case, this polynomial phi in the B's and C's. So these B's and C's are sort of playing the role of the second and third Chern classes of these CP2 bundles. And then there's a sum from 1 to n. Okay, so remark, if there is a rank 3 vector bundle such that the Chern classes are minus B and minus C, then this phi BC is just the tautological class of EI, where EI is the corresponding projective bundle. And then it just says that the tautological classes of E are just the sum of these tautological classes of the EIs. But in general, we don't know whether such a rank 3 vector bundle actually exists.
So, David?
Yes?
So do you know instances, of possible collection of, I guess, C2, some Chern classes that don't, some linear bundles that don't exist? In other words, I assume that the Chern classes that you get from linear bundles are not completely arbitrary.
Oh, so some B's and C's that don't come from a rank 3 vector bundle?
Yeah, and then most interestingly, but do come from some bundle with Fibre, a bunch of CP2s.
I don't have any examples. I guess it would depend on what the base is. I would imagine that I'd imagine there are plenty of bases B where any choice of B and C could be realized by a rank 3 vector bundle. But I'm also reasonably sure that some sufficiently complicated base, there'd be some that can't be realized.
Yeah, I don't know whether that was some standard calculation.
Yeah. Oh, I mean, even if the base is a sphere and you take like the Chern classes of a vector bundle, there's some divisibility condition on the.
Yeah, I guess from Bach periodicity.
Yeah. All right. Actually, I'll come back to this point a bit later. And then, so you notice here that I only took even powers of E. And that's because sort of E squared is P2, is a Pontryagin class, which is a stable characteristic class, whereas E is unstable. So when you have odd powers of E, something a little bit strange happens, is that so you get the sort of expected sum, but then you also get a correction. Now I haven't told you what these DIJs are. They're just they're just some degree 2 cohomology classes on the base. But the point of this formula is basically, if you had a family connected sum, you would get exactly this kind of formula. So if you compute tautological classes for a connected sum, you add up the tautological classes, but then you also have a kind of a correction which comes from sort of the P1 and E of the normal bundle of the section where you connect things together. So I'm not actually claiming that my family is a connected sum. I'm just saying that the formula for the tautological classes resembles a connected sum. All right, and then using these formulas, so there are some applications. So if you just look at CP2 or CP2 connect sum CP2, you can actually use those formulas to figure out the tautological ring. So in both cases, it's just a polynomial ring. For CP2, it's in kappa P1 squared and kappa P1 4, and in CP2 connect sum CP2, it's kappa P1 squared and kappa P1 cubed. I mean, you get something a bit better than that. You get a formula. You know, if I give you a tautological class, you can express it as some polynomial in these guys. Okay, and then another sort of application is you get these tautological relations. So, I mean, I just wrote down a few of them. Basically, so where do these relations come from? So these are all relations which are true for linear CP2 families. So we just did the calculation for tautological classes for a linear CP2 family, and you can just sort of check these formulas hold in that case. And then because of this theorem that the tautological classes in general look like a sum of linear CP2 families, then just sort of by linearity, these relations are going to hold. Okay, and one curious thing about that is that nowhere in this formula do you see n, the number of summands. So these formulas with exactly the same coefficients are true for all the definite four manifolds, which is kind of surprising, I think. All right, so now I'm going to talk a little bit about the proof, or the idea behind the proof. So basically, the idea came from thinking about you know, the proof of Donaldson's diagonalisation theorem, and then what would happen if you did it not for a single four manifold, but if you did it for a family. So just trying to think about the sort of the families. What is the family's analog of Donaldson's theorem? And in fact, there's more than one analog. So if you think about, you know, the Selberg-Witten proof, that you can generalize that, and that gives you a theorem. But you can also think about the instanton proof, and that gives you this result. So let me just quickly remind you how the proof of Donaldson's theorem works. So we have a definite four manifold X, and you consider the moduli space of self-dual instantons for an SU2 bundle whose second Chern class is -1 with a sufficiently generic metric. Then it's going to be a 5 manifold with some singularities. So the singularities look like cones over CP2, and you get basically you get a singularity for each reducible instanton, and the reducible instantons correspond to the classes in H2 that's square to 1, considered modulo plus or minus 1. And the moduli space is non-compact, but you can compactify it by adding these instantons which are like delta functions. So you compactify by adding a boundary, which is just a copy of X. And then that gives you a cobordism, because you basically remove a neighborhood of each singularity, and then you'll get a cobordism from X to a disjoint union of copies of CP2. And the number of copies of CP2 is exactly the number of pairs plus minus E that's square to 1. So here's the famous cobordism from X to these cones over CP2. So just remove these cones, you get a cobordism from X to copies of CP2. Now X is positive definite, so the signature of X is just B2. And signature is a cobordism invariant, so there must be n copies of CP2. So therefore there are n pairs E1 up to En that square to 1. Okay, but now those classes have to be an orthonormal basis, because Cauchy-Schwarz implies for I not equal to j, the EI inner product EJ is absolute value less than 1, but it's an integer, so it's got to be 0. Okay, so this is an orthonormal basis, and therefore H2 is diagonal. Okay, so now we think about what happens if you do this for a family. Suppose we have a smooth family with fibers this definite 4-manifold X, and assume for simplicity that the monodromy acts trivially on H2, and we consider the family's instanton moduli space. So basically you look at the moduli space of instantons on each fiber, and then you consider the union over all points B in the base, and of course you give that sort of the natural topology. So you get this big family's moduli space, and of course it comes with a forgetful map to the base. It's not going, in general, it's not going to be a fiber bundle, because as we move around in the base, the topology of the moduli space could change. So yeah, it's not necessarily a fiber bundle, but it comes with a map to B. And each fiber, what we can say is that each fiber contains n singular points. Oh, well, assume a sufficiently generic family of metrics, then each fiber is going to contain n singular points corresponding to the reducible instantons. And then I want to assuming some unobstructedness of the family's moduli space around the reducibles, you will again have this cone structure around the singularities. So now at each fiber of the base, the moduli space will look like a cone over CP2, but then this is happening in a family, so you'll have sort of a cone over linear CP2 bundles. So you'll have these linear CP2 bundles. All of this is assuming unobstructedness, and well, okay, I'll get to this point. I'll get back to this point later, but assuming that, we would have these linear CP2 bundles. And once again, you could compactify this moduli space by adding a copy of X on each fiber. And so as you do this in the family, it would be like adding a copy of E. So you would get this sort of family's version of the cobordism. So on one side, you've got E, and on the other side, you've got these linear CP2 bundles. And all of this is sort of relative B, meaning that there's this map to the base B.
David, excuse me.
Yes.
If you restrict to the cones, is it a
Yes.
fiber bundle? If you restrict to the right part,
Yes, assuming this unobstructedness result.
Okay,
Yep.
but it fails to be in general to be fiber bundle inside of the M bar, right?
Yeah, you would. That's what you would expect. Yeah.
Thank you.
So if this unobstructedness can be arranged, then you would get a cobordism relative B. So to say it's a cobordism relative B, I just mean it's a cobordism with a map to B, such that when you restrict over here, you get the original map to B, and if you restrict over here, you get these fiber bundles. And now it's not a. Now what I'd like to say is that the tautological classes are the same by looking at the vertical tangent bundle, but this is not necessarily a fiber bundle. So I don't really have a vertical tangent bundle, but what you can do is you can take, you have sort of a virtual, you have a virtual vertical bundle, because you just take the tangent bundle of M primed minus the pullback of the tangent bundle of the base. And the point is that the Pontryagin classes are stable, so you can still take the Pontryagin classes of this virtual vector bundle. So in other words, P1 of V and P2 of V, or E squared of V, makes sense. And if you restrict this virtual vector bundle to E, then you just get the vertical tangent bundle of the family. And likewise, if you restrict this virtual bundle to these CP2 bundles, you get the vertical tangent bundle. So these classes P1 and P2, when you restrict them to either side, you actually get the Pontryagin classes of the vertical tangent bundle. Okay, and then it just follows from Stokes' theorem, basically, that if you integrate P1 of the A e to the P1 of the A P2 to the B, or P1 of the A e to the 2B over E, it will be the same as integrating it over the disjoint union of E1 up to En. So you'll get that this tautological class is just the sum of these tautological classes of the CP2 bundles. So that's the idea. By the way, this sort of explains why for odd powers of E, the formula is not just a sum, is because the Euler class is not stable, and so you can't take the Euler class of this difference bundle. Okay, so once again, assuming unobstructedness of the moduli space, then we would get that the tautological classes of E are a sum of these tautological classes of these linear CP2 bundles. And then we did this calculation for what those tautological classes are, and they're just certain. There's just this given polynomial phi. So take this polynomial in the Chern classes of EI. So what are these bundles? What are these linear bundles? Well, for that you have to look at the deformation theory of the instantons around the reducibles. So basically, so let E1 up to En be the orthonormal basis, an orthonormal basis for H2, and so each of these classes there's a corresponding line bundle, and then of course there's a reducible instanton on L plus L star. And so you want to look at you want to look at the deformation theory of instantons around this reducible. So what you do is you take, well, if I was just doing this not for a family, if I was just doing this for a single four manifold X, I would take the index of the deformation complex. So the deformation complex is basically, you take the Atiyah-Hitchin-Singer complex and you tensor it with the adjoint bundle of this SU2 bundle. And if you are unobstructed, then so this complex has like H0, H1, H2, and if you are unobstructed, then H0 and H2 would be 0, and H1 would be 3 complex, would be real 6-dimensional, but it has a complex structure, and so it becomes a complex rank 3, a complex 3-dimensional vector space. Okay, but so then if you do this for a family, then basically you're taking the family's index of this deformation complex, and assuming unobstructedness, so assuming H0 and H2 are 0, then H1 would form a complex rank 3 vector bundle, VI, and then EI is just the projective bundle of that vector bundle. And so because VI is basically this family's index, then in principle you could compute its churn classes just by using Grothendieck-Riemann-Roch. So then once you've got the churn classes, you could plug that into the formula for the tautological classes, and then that would give you a formula for the tautological classes of E. Okay, but unfortunately, it's not clear, or at least it's not clear to me, that you can actually do this. So it's not clear that you can arrange unobstructedness of the family's moduli space around the reducibles. So of course, when you just do instantons on a single definite four manifold X, then it's known that you can, for a sufficiently generic metric, you get unobstructedness. But the proof is kind of complicated, and as far as I can tell, it's not going to work for a family. I mean, I don't have an example where it fails, but it doesn't. I'm skeptical that it would be true. Another way of thinking about it is, so I told you that this EI should be the projectivization of this family's index VI. And really the problem is that when you take the family's index, you don't get a vector bundle, you only get a virtual vector bundle, because the dimension of the kernel and the co-kernel could jump. So that's kind of the problem, is VI only exists as a virtual vector bundle and not necessarily as a genuine vector bundle. So instead of trying to make this work, we take a totally different approach, and we use Selberg-Witten theory. So it turns out that this results. So you can think of this argument that we've gone through as sort of a prediction of Donaldson theorem, Donaldson theory, that we couldn't quite prove rigorously. It turns out that you can actually do it using Selberg-Witten theory, and in fact you get something a little bit better than, you get a more detailed result. So I found this rather surprising that this works, because if you look at Selberg-Witten theory and you look at the moduli space, look at the family's moduli space, well, it's compact. So, there's no compactification. So there's no sort of obvious relation between that moduli space and your original family E. So there's no sort of cobordism in the same way. Okay, but nevertheless, it turns out that if you look at Selberg-Witten theory for this family, then you get some constraints on the topology of the family, and then you do, well, a whole bunch of calculations, and you ultimately get this relation on the tautological classes that we predicted. But I do want to mention that these computations are pretty lengthy, and I just would never have thought of how to do this if I hadn't known what the answer should look like using Donaldson theory. So I thought that was rather amazing so Donaldson theory could give you a prediction, and then you could sort of prove it rigorously with Selberg-Witten. Okay, so how do you prove it? So basically, so the advantage of Selberg-Witten is that we have sort of this Bauer-Furuta construction. So instead of cobordisms, we use cohomotopy, and of course these two things are related by the Pontryagin-Thom construction. But the good thing is, to get cobordisms, you have to worry about transversality and all of those sorts of issues. But with cohomotopy, it's all homotopy theoretic, and so you don't have to worry about any of that. Basically, so the way this works is, so you write down the Selberg-Witten equations with gauge fixing, in suitable Sobolev norms, and the equations will be a nonlinear map between Hilbert spaces. and then the Selberg-Witten moduli space would be the pre-image of a regular value of this map. Basically, what Bauer and Furuta do is that instead of looking at this this fiber of a regular value, just look at the map phi itself. Well, it's a map between Hilbert spaces. You could take the 1 point. Well, I shouldn't say 1 point compactification. You could add 1 point to make these into spheres, but of course those spheres would, because they're spheres of infinite dimensional Hilbert spaces, those spheres would be contractible, so you wouldn't get any homotopy information. But what you do is you take sort of a finite dimensional approximation. So you take suitably chosen finite dimensional subspaces and sort of take a finite dimensional approximation of the map, and then you take 1 point compactifications to get a map between spheres. And the homotopy class of this map contains interesting information. So after gauge fixing, there's still an overall S1 symmetry, and so S1 acts on these finite dimensional spheres, and this map F is equivariant. So basically, this map F gives you a class in S1 equivariant stable cohomotopy, and that's what's called the Bauer-Furuta invariant. And it's a refinement of the Selberg-Witten invariant in the sense that you can recover the usual Selberg-Witten invariant from it. And sort of one of the advantages of doing this is that instead of worrying about transversality, so in other words differential topology, we're just doing homotopy theory, so we don't have to worry about transversality issues. Now, okay, and now that was just for a single 4 manifold, but we can also do it for a family of 4 manifolds. So you consider once again a family, and then you sort of take finite dimensional approximation of the Selberg-Witten equations. And if you do this carefully, what you get is so instead of Hilbert spaces, you have Hilbert bundles, and you take finite dimensional subbundles. So those are finite dimensional vector bundles V and V primed, and then you get an equivariant S1 equivariant map between these sphere bundles that you get by taking the fiber-wise 1 point compactification. So this family's Bauer-Furuta invariant is basically a homotopy class, S1 equivariant homotopy class between sphere bundles over B. And then just purely from homotopy theory, you can get some constraints just from the existence of this map. So here is one version of this constraint. So suppose your family has a spin C structure on the fibers. Let D be the family's index of the spin C Dirac operator, and let D be the rank, or the virtual rank of D. Then the Chern classes of D vanish for J greater than D. So of course, this seems kind of silly until you realize that D is only a virtual vector bundle. So there's no reason, in general, the Chern classes could be non-zero for degrees higher than the rank. But what this theorem says is it says actually these are 0 for J greater than D.
Sorry, David?
Yes.
So what, maybe this must be something straightforward, but what does virtual rank mean here?
Oh, I mean just the rank in K, in the sense of K theory. So D is a different. So D is just, you know.
Oh, I see.
Difference
Like
of
the
vector bundles. So it's just the difference.
Essentially, the index, I guess.
Yeah, the index.
Okay. All right.
And so this result. So I mean, I don't really have time to give the proof. Basically, this result is well, it's one manifestation of sort of the family's Selberg-Witten proof of Donaldson's theorem, in a sense. So you look at the Selberg-Witten proof of Donaldson's theorem, and then you do it for a family of definite four manifolds, and you look at what you get, and this is basically, this result is what you get. So this result, I mean, this result looks very different. I mean, it doesn't say anything directly about the tautological classes, but these Chern classes are computed with Grothendieck, Riemann, Roch, and so indirectly they give you some relations on various Fibre integrals, and then that gives you some relations on tautological classes. So this is going to be just a sketch of the diagonalisation result, assuming this theorem. So suppose we have this family of definite four manifolds. So pick a basis for H2, then in fact you can lift those to classes in H2 of the family, that restrict to EI on the fibers, and such that if you integrate the cubes you get 0. So this condition here is just a kind of a normalization condition that makes these classes unique. And then you can also have a class nu, which is like a volume, which is like a fiber-wise volume. And these two conditions here are just sort of normalization conditions that make it unique. Then the cohomology of E turns out, so just a simple sort of spectral sequence argument. The cohomology is a free module over cohomology of the base with basis 1, x1 up to xn, and mu. Okay, so now you take a spin C structure on X and ds the corresponding Dirac operator. Then we had this theorem. So suppose that the index, or the rank of D, if you like, is 0. So C1 squared takes sigma is 0. Then this family's Bauer-Furuta theorem would just tell me that the index is 0. Oh, sorry, this should be rationally. So the index is 0 in K naught of B tens of the rational numbers. In other words, the Chern classes are all 0. Okay, so this condition is like saying C1 squared equals sigma, which is just n, and there are 2 to the n solutions. So basically, so C1 has to be a linear combination of E1 up to En, and the coefficients are all plus or minus 1. So that gives you, so there's 2 to the n choices. And then, so basically so the index of D is given by families of Singer. So e to the C1 on 2 times A hat. Okay, that has to be 0. So then, then if you expand out this exponential and then integrate all the terms, you'll get a whole bunch of integrals have to equal 0. And sort of a key point I want to highlight is that this relation for a single spin C structure doesn't tell you very much, but the fact that we can choose these epsilons to be plus or minus 1, so we get 2 to the n choices, so we actually get a lot of relations that way. And of course you expand out A hats, so the usual formula for A hat. So you expand all of that out, and you get a whole bunch of identities involving fiber integrals of this family. Okay, and then well, I don't want to go into too much detail, but basically, you also do an argument where for spin C structures such that the index is 1. So in other words, that corresponds to C1 squared takes sigma equals 8. And then, so sort of the rank is 1, and so the Chern classes have to be 0 in degree bigger than 1, and that tells you that the Chern character looks like e to the u, where u is C1. And so, you know, if you sit down and work out what u should be, well, okay, u has to be some expression like this. So, you know, the particular formula is not so important here. I just want to highlight that you get out of this vanishing theorem, you get a whole bunch of relations. And then those relations give you relations in the cohomology ring of E. So, so we define these classes Dij to be the integral of xi squared xj. Then the cohomology ring has to have basically you can write down the cohomology ring entirely in terms of these Dijs. Okay, there's some other classes Gi, Ji, omega, but those are certain polynomials that you can write down in Dij. So basically, the entire cohomology ring is just given by some formula in terms of these Dijs. So everything is now pretty explicit. And likewise, the Pontryagin class and Euler class of the tangent bundle, you can work out what those are. So again, they're given by some explicit formula. So P1 is 3 times x1 squared up to xn squared plus mu, where mu is a certain polynomial in the Dijs, and it works out to be this tautological class here. And likewise, there's a formula for E. And so if you use these formulas and you use the structure of the cohomology ring, then basically you can evaluate all of these integrals. So as you can imagine, you know, there's a whole lot of algebra that goes into doing this evaluation, but you can, in the end, you can do it. So yeah, so basically there's as a consequence of the structure of the cohomology ring, you get a formula like if I take some polynomial in the x's and I take its fiber integral, it turns out that it looks like a sum from 1 to n of fiber integrals of fj, where fj is given by sort of specialization of f. And this somehow, so this fact that just sort of comes from the structure of the cohomology ring is somehow a reflection of this diagonalisation. So you know, these fiber integrals are splitting up into sums from 1 to n. And okay, and then so if I have my tautological class, well, it's some fiber integral P1a e to the 2b, and then that splits up because of this relation, that splits up sum 1 to n. And yeah, you take the formulas for P1 and E, and then you specialize them, and you get these formulas. Now, if you recall way back earlier in the talk where we looked at linear CP2 bundles, you know P1 and E for a linear CP2 family looked exactly like these guys. So this formula on the right looks exactly like the sum from 1 to n of tautological classes of a CP2 bundle, where B and C are certain polynomials in Dij. So I'm not going to give you the formula because it's quite complicated. But anyway, it's some explicit formula. And another interesting fact is that you also get these relations. So xi cubed equals bixi plus ci. So exactly what we saw for a linear CP2 family. So this family E is somehow has some sort of structure that resembles CP2 linear CP2 families. Right. So this gives you this basically gives you the formula. And then you can do the same. Then you can do the same for odd powers of E, but there are some correction terms. So I mean, I don't think that there's not really much point going into it. I just put this formula here just to illustrate, what the formula looks like. So you do these Fibre integrals and you get some term like that, and you get a formula which looks exactly like what you would get for a connected sum of families of CP2. Okay, so yeah, I'll stop here.
Are there any questions?
Yeah, so my understanding is that you would like to have these kappa classes at the end as classes in cohomology of the classifying space of the diffeomorphism group.
Yes. Yep.
Diffeomorphism group.
Yeah.
Please kind of explain us one little thing, that in the construction you assume that pi1 of x of the base acts trivially on the Fibre.
Oh, yes.
On cohomology. That since we do not know quite well diffeomorphism group, we do not know if fundamental group would act trivially on.
Yep. So okay, so basically, because we're looking at definite four manifold, so so homeomorphic to a connected sum of CP2s, and the monodromy has to act by isometries, but the H2 is just diagonal. The isometry group just ends up being a finite group. All you can do is you can permute the summands and also plus and minuses. So so there's at most the monodromy would act through this finite group, and sort of basically because we're working rationally, it's enough to restrict to the case where the monodromy is trivial, because yeah, you look at the subgroup of the diffeomorphism group which acts trivially on H2, and that has finite index.
Yeah, Torelli group. Okay.
Yeah.
Okay. What is the, so you can lift this kappa classes to the cohomology of the classifying space, or
yes.
Not? Okay. Yeah. Okay. This is, and via Torelli group.
Yes. Yeah.
Okay. Thank you.
So, go ahead, Ali.
All right. Sorry. In the definition of this canonical classes, you can also work with other coefficients, right? Like, let's say Z mod 2, and take Selberg-Witten classes to define these classes, these accuracy classes. Is it something interesting to do, or to get interesting cohomology classes?
Yeah. Okay. So there's a couple of reasons why I use rational instead of, say, integral, because basically I want to apply this family's index of a Dirac operator, and I need a spin C structure, and in general you don't quite have one, but sort of, if you work rationally, you can sort of get around that problem. Whereas if you work integrally, you can't quite do it. So if I used integral coefficients, then yeah, life would be very difficult. But you could perhaps use, say, you know, Z mod 2, and that potentially could be very interesting, because the you can do the Selberg-Witten theory, and you would potentially get some relations there as well. I just haven't thought about it in great detail. Yeah.
Thank you.
Yeah, would you comment a little bit on the proof of the main technical theorem that you kind of you assume to be just used? So about Chern classes.
Oh, okay. Yeah.
What is the key observation here?
Right. So so basically, you have this Bauer-Furuta map, which is this equivariant map between sphere bundles. And basically, you look at the fixed points of the S1 action. And because our and in general, the fixed points is a sphere of lower. In general, the fixed points is a sphere of dimension B plus, or, well, actually, yeah, actually, I should say, I actually look at Selberg-Witten with the opposite orientation. So the fixed point is a sphere of dimension B minus, B2 minus, which, because it's a definite four manifold, it's just a zero sphere. So basically, yeah, so you look at, so basically it comes by looking at the fixed points under the circle action. And that sort of gives you a commutative diagram, because you look at the restriction of F to the fixed points. And then you do an argument involving Thom isomorphism. And that gives you a statement in S1 equivariant cohomology of the base, involving the equivariant Euler class of the Dirac operator. But the equivariant Euler class of the Dirac operator can be expressed in terms of the Chern classes, and that gives you this vanishing.
Okay, so the positive definite so you use definite there, because it's yeah. Do you think there is something like this is true for arbitrary four-dimensional?
So there's a version of this theorem that works without the definite assumption, but you need to assume a rather strong condition, which is that if you look at the bundle H2 plus, or actually, because I'm reversing orientation, look at the bundle H2 minus, and you want that the Euler class of that bundle is not zero.
Okay.
So what's happening here in the definite case is that bundle has rank 0, so its Euler class is just 1. And you see, if we had some family and we restricted, if we assumed the monodromy of our family was trivial, that bundle would just be trivial, and its Euler class would be 0 if its rank was bigger than 1. So there is an analog of this theorem, but it's not clear that it can be used to say anything about tautological classes.
So directly, it does not. This theorem does not involve the Selberg-Witten.
This theorem on this slide.
So this theorem directly does not involve the Selberg-Witten modular space.
Yeah, that's correct.
So then you can actually take stabilization of X, right? So you take, so what happens if you take connected sum with S2 cross S2?
Oh, well then as soon as you take even one stabilization, you're not definite anymore.
Okay.
So yeah, unfortunately,
Okay.
it just kind of sort of breaks down immediately.
No, okay. So no, I'm okay. I understand. Thank
Yeah.
you. I'm just
Yeah.
wondering.
So even, oh, sorry, go ahead.
I'm just wondering how this construction survives and you try to stabilize in one way or another.
Yeah. So it's very much, yeah, this result is just not going to survive stabilization.
Okay, that's very interesting. Thank you.
So maybe I'll just comment that, okay, I would be very interested to know the tautological ring for S2 cross S2. So that's not known. All that's known is this computation of Randall-Williams. It shows its, you know, its Krull dimension is 3 or 4.
Yeah. No, it's interesting that here you essentially don't use any geometrical features of your manifolds except, you know, Selberg-Witten, but you know, in so I noticed that in some other work you use essentially for say K3 surface, it was very important. So,
Yes. Yeah.
would you care to share some thoughts about some geometry here?
Yes, I haven't thought about that, but so if we were looking at connected sums of CP2s, I mean, they have positive scalar curvature metrics, so maybe that could be used somehow. Of course, they're not. Of course, they don't have. Of course, they're not going to have symplectic structures or anything. But yeah, they have positive scalar curvature metrics, so maybe that could be used. I don't, off the top of my head, I don't know how, but that's what I would look into if I was going to try to do some geometry with them.
Yeah, so connected sum of CP2s would have also Ricci flat, Ricci positive metric as well.
Yeah.
Well, anyway, so thank you so much. It's actually very interesting. I'm sorry, so I take all the
No problem.